Number 10, strong bases. What did you put?
At first, I took when I looked at the notes for the lab, and it says like bases, hydrogen lines are ionized, but the strong bases have one of those different percentages.
For all bases hydrolyze. So, for example, even a weak base like ammonia, ammonia does not ionize. It's a weak base, so you think it partially ionizes, but what would it partially ionize into? And whether it's a strong base or weak base, all bases hydrolyze with water. And so just ammonia partially hydrolyzes, so it's favored in the reverse direction to make ammonium and hydroxide. Strong bases are the same, like amide. What does amide hydrolyze or ionize into? It doesn't ionize. Amide doesn't ionize. Amide does what? Amide is a strong base, therefore strong bases completely hydrolyze in water. So ammonia produces just a little bit of hydroxide, whereas amide produces a lot of hydroxide. Because amide is going to make ammonium and hydroxide. And so this is downhill. This is favored here. This is uphill. So we get very little hydroxide. Does that make sense? And so this one is all bases don't ionize. So they just hydrolyze. B is the correct answer for that. Okay, other questions?
Well, that doesn't say all bases, it's strong bases. So
strong bases and weak bases. No bases.
But if I think of like sodium hydroxide and I put down water, it does dissociate into
Sodium hydroxide is a sodium salt. So sodium hydroxide is a sodium salt. And sodium salts are all strong electrolytes. And strong electrolytes ionize. But what's the base part of it is hydroxide. Do you see sodium hydroxide on the strong base part of the chart? Well, then it must not be a strong base. If it's not one of the strong bases listed there, it must be a weak base. Is that correct? So the situation is, this is why we define the strong bases a little differently. The strong bases are soluble hydroxides. And so I talked about this before. The same goes for sodium oxide, sodium amide, all these. The strong base is this. And so if you're saying, okay, sodium amide is a strong base, therefore what species are in solution? You'd say sodium ions and amide ions, and then you stop there. Sodium amide, yes, that's a strong base, but the first thing is we treat it as a soluble salt. And then we get sodium ions and amide ions. Amide ions are the strong base. This is the strong base. So this is strong bases hydrolyze water. And so you have to treat it separately. It's not. And so the first part is a soluble salt. Second part is the base. Okay, other questions? Mm-hmm. You just look at the properties. What properties stand out? So, for example, HCl, HBr, what are the properties that stand out in HCl and HBr? Obviously there's redox, there's metathesis, but what property really stands out for those? And in fact, if somebody asks what are the chemical properties of HCl and HBr, most people will just say they're both strong acids. So that stands out. HF is a weak acid. So what we see there's a mixture of acids. What do acids want to do? They want to donate their proton. Do you see any bases in there? No. So the only thing they can donate is to water. But when you look at this next one, what's a property that stands out for KMNO4? Yeah, which means
Very,
hmm,
very reactive.
very reactive. KMNO4 is extremely reactive in what way? Acid-base metathesis or redox? Redox. And we call it a powerful oxidizer. It's electron poor. It's actually ranked number 3 on the chart. You see fluorine at the bottom right? Those hydrogen peroxide is number 2 on the chart, and number 3 on the chart is permanganate. It's number 3 powerful oxidizer. On this chart, on our chart, it's a little bit different. I think it's number 5. Well, it's a powerful oxidizer. And what do you know about this? CH3OH, what's that called? Methanol. And what do you know about methanol? Now we're talking about redox because that's what stands out about KMNO4, not its metathesis, not its acid base, but its redox properties. And what do you know about the redox properties of CH3OH?
The carbon is electron rich.
Carbon's electron rich. Methanol is electron rich. So you have electron poor and electron rich. What's going to happen? It's going to react. This is potentially explosive. Is this explosive if you have a bunch of acids that want to donate, but there's nobody to donate to? Is that explosive? No. And so which of these combinations is least stable? A, for sure. A just stands out being unstable. Okay, other questions? All right, this whole exam was in 2017. I did a sequence a little differently. In 2017, I didn't cover all the reactions at once. I think I only did metathesis and some others. So there are very few chemical reactions on these old exam 1 and old exam 2. Very few chemical reactions. On your test, you're going to have a lot more chemical reaction problems. The chemical reaction problems are going to be similar to the worksheet that I handed out the other day. So you'll want to work through those to prepare for the test next week. And so you're going to have a lot more chemical reactions. What you won't have are energy calculations. So like number 36. Number 36 won't be on there. 35, no. 34, no. 33, no. 32, no. 31, no. 30, no. 29, no. 28, no. Oh, no, 28. 28 is gases. So 29 through 36, you aren't going to have anything like that on your test because we're not covering chapter 7. Our exam is just going to cover chapters 4, 5, and 6. Okay. The problem with chapter 5 is you look at the homework, there isn't that much practice for predicting chemical reactions. And so that's why I gave that worksheet. The worksheet you don't have to turn in as homework. But you should do it though. All right, any other questions? I need to finish up. I want to finish up chapter 6 today. So we talked about gas pressure, did we? Pretty much. Where did I leave off? Oh, 117, we did that? Okay, the pressure, barometric form. Did I talk about liquid pressure? Okay. I talked about like 30 feet of water. Did we calculate it? It's approximately 30 feet, but did we calculate it more accurately? No? Okay. All right. If I have, how many miles of air was that per square inch? 60 miles. 60 miles? air? 60 miles. A lot. It's so high. See, if we're 60 miles at the bottom of this air, then that's 14.7 pounds per square inch, correct? And so you have 14.7 pounds of air. If we were at 30 miles, would it be half the weight? No, it's not half the weight. Why? Yeah, the density changes. It's non-linear. You know? That's different than liquids. You know, the density of liquids doesn't really change that much, right? And so this would be 14.7 pounds per square inch of air. And then if I had water, water is a lot more dense than air, like 1,000 times more dense. If water is 1,000 times more dense than air, then will I need 1,000 times less? Actually, I'll need a lot less than 1,000 times. I'll only need 30 feet. Because what we can assume is that the density of water doesn't change much in 30 feet. And so the density at the top of 30 feet is about the same as the density at the bottom of 30 feet. It's going to be slightly different because, you know, it's going to be compressed more, a little bit more at the bottom, but it's not going to be that significant. And so 30 feet of water, H2O liquid, is going to weigh 14.7 pounds per square inch. What about 15 feet? If I was at 15 feet of water, would that be half as much weight? Half as much pressure? Yes. The answer would be yes, because it's fairly linear. Just air being a gas is different. And so the pressure, actually we can calculate the pressure of the liquid. The pressure of the air had that, the barometric formula, which is kind of complicated. But the pressure of the liquid is a lot easier. The pressure of a liquid, since the density is not changing, is just equal to the density, which stays fairly constant, times the force of gravity times the height. Since the density doesn't change much, then if I have half the height, I have half the pressure. If I have 1/4 of the height, I have 1/4 of the pressure. So the density and the G is a constant, so this is just equal to a constant times the height. And the height is 30 feet here, in this case. Whereas you can't do the same with air, you know, because yes, we need a little more complicated equation for that. And so this would be just the density of water, right? That would be it. Now we could have more dense liquids, you know, because what's the most dense liquid you can think of? Mercury. Mercury is the most dense. And do you know how many times heavier it is than water? It's 13.6 times heavier. Actually, we can be more precise here. How many times heavier it is? I use 13.6, but if you wanted the more sig figs, here it is. In chapter 6, 13.5951 grams per cubic centimeter at 0 degrees C. Mercury expands a little bit with temperature because it's metal. And so if the barometer has been calibrated at 0 degrees C, we have to correct it. But we didn't use a barometer. And so we don't need any kind of correction in the KClO3 experiment. This is G to 6 sig figs. So the gravitational constant is 9.80655 meters per second squared. It's our G. And so those are constant times the height. Now, if mercury is 13.6 times heavier, then we'll need 13.6 times less. And so we'll need about 3 feet roughly, of mercury. In fact, less than 3 feet. You know how much we'll need for the mercury? We'll just need 760 millimeters, or about 3/4 of a meter of mercury. That's going to weigh 14.7 pounds per inch squared. And so what I did was I said this is approximately 30 feet. And so what we could do is a quick calculation. All these pressures are equal here. The air, which is 60 miles, the water, which is 30 feet, and the mercury, which is 760 millimeters. So what we're going to do is we're going to get this number more precise. Is it really 30 feet? Is it right on there? And so this is the way we're going to do it. We're going to set the pressure of the liquid water equal to the pressure of the mercury. Yeah. The pressure of liquid water is equal to the density of water times G times the height of the water column. This is going to equal the density of the mercury times G times the height of the mercury. The height of the mercury, we know, under normal atmospheric pressure at 760 millimeters of mercury, or 760 millimeters. And then we're going to solve for the height of the water and see if it comes out to 30 feet. So the height of the water that's going to be equivalent to 760 millimeters of mercury will equal the density of mercury over the density of water times 760 millimeters. The density of mercury we'll just take as 13.5951 grams per milliliter. And the density of water we'll take as 1.00 grams per milliliter times 760 millimeters. And so what does that come out to? How many millimeters of water will we get? Well, about 13.6 times. So can somebody calculate it?
Professor, is that a 4 or a 9 and a 13.5?
9.
Okay.
9.5951.
You want it in millimeters? Or?
Yeah, we'll just go with millimeters. How many?
10,932.276.
All right, we'll just go with 10,332 millimeters, which is 10.3 meters of water. And there's about 3 feet in the meter. And so that's why it's at about 30 feet. Right? And so this is about 30 feet. This is more precise though, 10.332 meters. How many sig figs are we allowed? 3? Yeah. 10.3 meters is approximately 30 feet. Okay, did I talk about the swimmer swimming under the ocean? No?
Yeah.
How many atmospheres? Okay.
2 ATM.
Yeah. Okay. Okay. So this is how it works. On one side of this, we could have the air. On the other side, we could have the water. So if we made a barometer out of water, how tall would the barometer have to be? If we made a barometer out of water, it'd have to be 30 feet tall, because this is how a barometer works. A barometer is you put a pool of liquid in here, and then in this, what we're going to do is we're going to put a column of water. And this pool will be water here. And so we're going to have two things. On the outside here, we're going to have air. On the inside here, we have water. And what's going to happen is it depends on which one weighs more. Does the air weigh more or does the water weigh more? Here. If the water weighs more, then it's going to push the water out of the tube into the pool and lift this up here. In other words, lose some. If the air weighs more, it's going to push the water up. And so to make this equal, what we're going to have is this. If we use a water barometer, this water column would be 30 feet tall, or 10.3 meters. Would be equivalent to 60 miles of air. And they both weigh the same amount, 14.7 pounds and 14.7 pounds. Well, 10.3 meters is too tall. And so even though mercury is toxic, it's a heavy metal, we're going to use the mercury. And so when you look at the bottom of the barometer sits in a pool of liquid mercury. And then we have mercury in a tube here. And so outside we're going to have our air, 60 miles of air. But inside, since mercury is so much more dense, we're only going to have 760 millimeters of mercury. Yeah. And both are going to weigh 14.7 pounds per square inch. Here, there's no air in here. This is a vacuum. And so we don't have to worry about how much the air inside the tube weighs in the vacuum. So if the air pressure goes up, it's going to force the mercury up higher into the tube. If the air pressure goes down, the mercury is going to leak out of the tube. And so we're going to see changes. And so basically, when we do pressure, millimeters of mercury is not a pressure unit. Millimeters of mercury is the height, but the pressure is going to equal a constant times the height. And so, in other words, we'll just say the pressure is directly proportional to the height. But the height is not force per unit area. And therefore, we're missing, in order to convert it back to real pressure, we need the constant, which is going to be the density times G. And then we can convert the millimeters of mercury to Pascal. Does that make sense? And so it's kind of weird, but we measure the pressure of gases by the height of the mercury column. And so here we see this is the barometer. This vacuum up here. So the weight of the atmosphere is equal to the weight of the mercury. The weight of the atmosphere is equal to the weight of the mercury. The weight of the atmosphere is equal to the weight of the mercury. Okay. And then we have different units. One atmosphere is actually defined as 760 torr. But when we do the physics of this, it's almost the same as 760 millimeters of mercury. It's just slightly different. And I talked about Pascal, did I? Already? Okay. But we don't really have to worry about the small difference between torr and millimeters of mercury. We just take them as the same. And so in this text, we will use the pressure units of torr and millimeters of mercury interchangeably. Unless you're doing highly accurate work. If you do highly accurate work, then we have to worry about it a little bit. This is a mercury manometer. When the two liquid levels are equal, that is, the liquid level with the trapped gas in here is equal to the liquid level out here with the atmosphere, then what does that tell you? That tells you they both weigh the same. And so the pressure outside is equal to the pressure inside. Do you see that? However, if the two levels are skewed like this, let's say the gas level is lower than the atmosphere. This means the pressure of the gas is greater than the barometric pressure. And what it is it's going to be the weight of the atmosphere, or the weight of the air, plus the weight of this is mercury. And so if we combine the weight of the atmosphere and the weight of the mercury in millimeters of mercury, then that's going to equal the pressure of the gas here. I do the equations a little differently. So this is the way I do it. Petrucci doesn't like negative signs in these equations. And so he makes delta P. So for example, delta P in one instance will be positive, and delta P in another instance will be negative. I don't like this way of doing it. And so the way I like to do it is like this. So if the two liquid levels are the same, then we know the pressures are equalized. And so we look at the mercury here. Outside here, we have the barometric pressure, so the pressure of the barometer. And inside here, we have the pressure of the gas. And so since the two levels are equal, the pressure of the barometer, that is atmospheric pressure, is equal to the pressure of the gas. So we'll just read the barometer, and that will be the gas pressure. In the next scenario, the pressure of the gas is greater than barometric pressure. It weighs more. So here, what we'll do is we'll set up a balance like this, a seesaw. And if the seesaw is horizontal like this, then that means both sides weigh the same amount. And so over here on the right, I have the pressure of the gas. Over here on the left, I have the pressure of the mercury plus the pressure of the atmosphere, or the barometric pressure. And so the equation I'd like to write for this is this. One, the pressure of the barometer is less than the pressure of the gas. Two, the pressure of the barometer, barometric pressure, plus the pressure of the mercury is equal to the pressure of the gas. Three, therefore, the pressure of the gas is equal to the barometric pressure minus the pressure of the mercury. Oops, what am I doing? No, I don't need to do this, sorry. I jumped ahead. Therefore, the pressure of the gas is equal to the barometric pressure plus the pressure of the mercury. This is where I should have stopped. The third scenario is that one here, where the atmospheric pressure weighs more than the gas. And so you can see the seesaw is tilted. Since the seesaw is tilted, the atmospheric pressure is heavier than the gas pressure. And so here, the pressure of the atmosphere, or barometric, I should use barometric since they're using barometric. The barometric pressure is greater than the gas pressure. And so that's the tilted seesaw. Then what we do is we make it horizontal. So we make a level seesaw here. And so what that means, if we make it level here, the atmospheric pressure, or the barometric pressure, is equal to the pressure of the gas plus the pressure of the liquid mercury here. So the barometric pressure is equal to the pressure of the gas plus the pressure of the mercury. And now we're going to solve for the pressure of the gas. The pressure of the gas is equal to the barometric pressure minus the pressure of the mercury. So I'd just like to derive it. Here, Petrucci always has one equation. Pressure of the gas is equal to barometric pressure plus delta P. But he has two different delta P's. You use this delta P for this scenario, and you use this delta P for that scenario. But I don't particularly like it. I just like to do it like this, the same method. Just following those. All right, that's a manometer. There are other ways to measure the pressure of a gas. You know, one of the ways is to measure the thermal conductivity of a gas. You know, and so what they do is they heat up one probe and then measure if that heat is felt by another probe. So one probe gets hot. And the situation is, if there's no gas, then the heat can't be transferred because heat is kinetic energy. So if one of the probes is hot and there's no air to transfer that kinetic energy to, then it's going to go nowhere. And so this would be like a perfect vacuum. In a perfect vacuum, there's no thermal conductivity because there's no gas to transfer the kinetic energy from one side to the other. And so if we had like a thermos, you know, a vacuum thermos, if you had a perfect vacuum thermos, your coffee would never get cold. But if gas molecules are there or they leak in there, then what's going to happen is those gas molecules now can transfer the kinetic energy. Because if one piece of metal is really hot, it's vibrating quite a lot, which can transfer that kinetic energy by collisions to the gas. And the gas can transfer that kinetic energy to the other probe by collisions. So we get heat transport. So there are other ways of measuring pressure, excuse me. Than those. Okay, what else are we looking at in this chapter? Okay, gas pressure, and then we're going to go to the simple gas laws. We combine the simple gas laws into the combined gas law and the ideal gas equation. And we'll look at some applications of the ideal gas law. Do you remember the simple gas laws? Like Charles' law? Probably Charles' laws. Charles' law, Boyle's law, Galen-Sachs law, Avogadro's law. Do you guys remember those? You don't have to. But Charles' law is a good one to know because Charles' law tells us what about temperature? Volume is proportional to temperature. So Charles' law makes a plot. You know, so Charles' law is good because volume is directly proportional to temperature. So if we increase the temperature, the volume increases. But likewise, if we decrease the temperature, the volume decreases. What's the lowest volume possible? Zero. So when the volume gets to zero, what is the temperature? The temperature is 0 degrees C? Absolute zero. So this will be 0 Kelvin, which is not 0 degrees C. What is it? Yeah, minus 273.15 degrees C. So if somebody said that they got to minus 300 degrees C, is that possible? No, that's impossible because that's lower than the cold. You can't go to negative volume. The smallest volume you can have is 0. And therefore, the smallest temperature we can have is 0 Kelvin, or absolute zero. So Charles' law was important in figuring out the absolute temperature scale. Charles' law. Some standardized exams will ask you, Boyle's law and this kind of stuff, but I'm not going to ask you. Instead, what we're going to do is we're going to take all these simple gas laws. Avogadro's law is important too. Let me just briefly mention Avogadro's. Avogadro's law just says that the volume is directly proportional to the number of moles of gas. So if you have twice as much gas, you're going to have twice as much volume. All else being equal, that kind of thing. And that's Avogadro. And then what we're going to do is we're going to combine these. So I'll say Charles' law, etc. We combine these to get the combined gas law. The combined gas law is a little bit different than your Chem 1 or Chem 4 version. Because we're going to incorporate Avogadro's law. And so the moles are going to be incorporated. In Chem 4, it's just P1 V1 over T1. In Chem 1A, it's P1 V1 N1 T1. And so what this allows us to do is it allows us to recalculate things if we lose some gas. Let's say some gas is lost. What happens to the pressure or the volume? Or if we add additional gas. And so the number of moles of gas changes by addition or loss of gas. If we lose half the gas, then we should have half the volume. That's basically what it's saying. Okay, we can also get the combined gas law. We can also get the ideal gas law from this, because this is equal to constant. Do you know what that constant is called? R. And R is 0.08206 units. Liters times atmosphere per mole times Kelvin.
Do we need to know all the constants for the next test? Like memorize the constants?
No. There's another R value. The other R value is in different units. It's 8.3145 joules per mole Kelvin. So most people memorize these two. Do you have them memorized? No. What's the difference between this one and this one? This one has liters atmosphere. This one has joule. So it's kind of weird. Do you know a liter times an atmosphere is equal to energy? Did you know that? Because joule is energy. You guys know joules, right? So how's a liter atmosphere energy? And the way to think about this is this. Does it cost energy to blow up a balloon? How much energy does it cost? Well, how much energy depends on two things. What two things does it depend on? It depends on how big the balloon you want to blow up is. It's a huge balloon or a small balloon. If it's a small balloon, it's going to take less energy. And so we need to know how many liters you want to blow that balloon up by. 1 liter, 2 liters, 3 liters? So if you're going to blow up 3 1-liter balloons is going to cost you 3 times as much energy as blowing up a 1-liter balloon, right? The other thing it depends on is where are you blowing it up? If you blew it up, is it easy to blow up a balloon 30 feet underwater? No, because you'd be blowing it against how many atmospheres of pressure? 2 atmospheres. It'd be a lot easier if there was 0 atmospheres, right? If there was 0 atmospheres, have you ever seen a balloon expand in a vacuum? You wouldn't really have to do much, And so it depends on the external pressure. Are you blowing it up underwater? If you blew up a balloon 30 feet under H2O, that's one thing. But if you tried to blow up the same balloon under 30 feet of mercury, you probably wouldn't be able to blow it up. Right? I don't think you'd have trouble blowing it up under 30 feet of water, I think. You'd die. I mean, you wouldn't be able to make it. Yeah. There. And so that's energy. So what we can do is we can do this. We can take 0.08206 liters times atmosphere per mole times Kelvin and divide it by 8.3145 joules per mole Kelvin. And this is going to tell us how much energy it takes to blow up a 1-liter balloon against the pressure of 1 atmosphere. To blow up a 1-liter balloon against a pressure of 1 atmosphere costs us 101.3 joules. Per liter. Oh, oops. I screwed it up. Sorry. I need to flip this. Flip it over. This is joules per liter atmosphere. Flip it. Sorry. And so 8.3145 divided by 0.08206 gives us 101.3. And so oftentimes people will memorize or have these memorized. Or if you know this conversion factor, you don't have to memorize this. If you know this conversion factor, then we can convert this R into this R just by canceling out the liters of atmosphere and multiplying by joules. So about 100 joules to blow up a 1-liter balloon against an external pressure of 1 atmosphere. So this is called the ideal gas law. And so what we're going to do is we're going to get rid of this fraction and just go PV is equal to nRT. PV is equal to nRT, and most people can memorize this. The ideal gas law. What do they call it? They call it the ideal gas equation. So let's take a look at applications of the ideal gas law. The first application is just solving for one variable, given the other. This is just algebra. So we solve for volume, temperature, moles, or pressure, given the other 4 or 3. That's the most common application. And you've probably done a bunch of these calculations. The next application that's pretty useful is molar volume. Which I'm going to just call MB. Molar volume is how many liters per mole of the gas. And so if I had 1 mole of gas, do you know the molar volume? Did you have to memorize this 22.4 in Chem 4? 22.4 is the volume, molar volume of the gas at STP. But we can calculate it. So if I take V divided by N, V divided by N is equal to RT divided by P. And so this is equal to RT over P. And so the equation is molar volume is equal to RT over P. So I can figure out the molar volume of any gas as long as I know the temperature and the pressure. In fact, all gases will have the same molar volume at that given temperature and pressure. And so we have different molar volumes here. I have to memorize the molar volume at STP. Have you ever heard of STP before? STP stands for, standard temperature and pressure. What is the standard temperature?
Didn't you say last semester in Kemper that it changed because it wasn't at 1 atmosphere?
Oh, the pressure changed, yeah, but the temperature didn't. Standard temperature is the same. What is it? No, that's 0 degrees C. It makes sense that, do you know why they calibrate barometers at 0 degrees C? They calibrate barometers at 0 degrees C because does anybody work at 0 degrees C? Not really, unless it's outside barometer. Most people, when they're working in the lab, it's a lot warmer, right? And so, well, why not pick 25 degrees C? They should calibrate it at 25 degrees C. But the problem with calibrating it at 25 degrees C is this. Mercury expands and contracts with temperature. So if they calibrated the barometer at 25, then anything above 25, it expanded. Anything below 25, it contracts. And so what that means is the correction is going to be minus at temperatures above, and the correction is going to be plus at temperatures below. That's a hassle. That's like what Petrucci did, you know. Okay, you have to use a positive for this scenario, you have to use a negative for this scenario. Do you want to deal with that? No. So if they calibrate the barometer at 0, then the correction's always minus because we're always working above 0. And so if you have a mercury barometer, you just look up in the correction table how much you need to subtract it due to expansion of mercury. This doesn't make so much sense. I learned STP in Chem 4. And I'm memorized the molar volume of gas, you know, at pressure. Now the pressure, standard pressure, the old standard pressure is 1 atmosphere. The new standard pressure is 1 bar. This is the old, and this is the new. So I measured the molar volume of the gas from the old, and I had it memorized. The molar volume is equal to 22.4 liters per mole. Is that right? I forgot it earlier. I forgot it, and then my memory was refreshed. You see this 22.4? I memorized that in Chem 4. How many times have I used that since Chem 4? 0. It's a totally worthless number. Totally worthless number, but I had it memorized for so long. And it took me time to memorize. It wasn't so easy to memorize. Turned out the only time I used it was for the test. What is the molar volume at STP? 22.4. That was the first and the last time I used it. It wasn't worth memorizing at all. So I'm not even going to bother memorizing the new STP molar volume. You know, what is the new? Well, what's bigger, 1 bar or 1 atmosphere? Let me tell you this. Do you recall the conversion factor here? The conversion factor is 1 atmosphere is equivalent to 1.01325 bar. So what is bigger, an atmosphere or a bar? Okay, a bar is a little bit smaller because we need more bars to make 1 atmosphere. Does that make sense? So if I had 1 bar, would it be greater than 1 atmosphere or less than 1 atmosphere?
Is 1 atmosphere 1.00000? Is it?
Yeah, this is exactly 1 atmosphere. These are exact. We could do the algebra. It's going to be 1 divided by 101,325. And so 1 bar is just slightly less than 1 atmosphere. So if 1 bar is a little bit less pressure, what happens to the volume? It expands. And so this should be a little bit bigger than 22.4. What is it? Well, okay, we can calculate it. So the molar volume at the mu STP is equal to R 0.08206 liters times atmosphere per mole Kelvin. T, which would be 273.15 Kelvin, over P. P is 1 bar. Note the units don't quite work out. Do you see the atmospheres and bars? So either I convert atmospheres into bars or I convert bars into atmospheres. Which one do you want to do? The one in the numerator or the one in the denominator? Let's do the one in the numerator. So I'm going to convert atmospheres into bars. So I'll do 101,325 bar per atmosphere. Okay, now let's look at the units. So Kelvin cancels, atmospheres cancel, bars cancel, and I'm left with liters per mole. And that's what I want. Liters per mole. .08206 times 273.15 times 1.01325. 22.7. So this comes out to 22.71. I'm allowed 4 sig figs, so I'll just add one more. Liters per mole. In other words, it comes out to 22.7 liters per mole. This is the old molar volume. The old. This is the new molar volume. 22.71. Do you want to memorize that? No. Don't memorize the old, don't memorize the new. Why? They're easy to derive and you don't use it ever. Maybe you will. I don't know. Well, I didn't.
If we solve problems on you want us to use them
Normally we don't do chemical when we do a gas problem, normally it's not going to be at 0 degrees C. It's going to be at some other temperature. And you know what the most common temperature is? Not 0 degrees C. The most common temperature would be 25 room temperature. And so if you're going to memorize one, memorize this one. Don't memorize those. This one's worth memorizing because this is the molar volume at RT, room temperature, and RP, room pressure. What's room pressure? RT and P. Room pressure would just be normal pressure. What is normal pressure? 1 atmosphere. And so RT is going to be 298.15 Kelvin. RP is going to be 1 atmosphere. We'll just call it exactly 1 atmosphere. And therefore, the molar volume is equal to RT over P. And that's going to be 0.08206 liters atmosphere per mole Kelvin times T, 298.15 Kelvin, divided by P, 1 atmosphere exactly. Let's see. Atmospheres cancel, Kelvin cancel. That leaves us with moles, and this comes out to, can somebody punch that out? .466 liters per mole. We're allowed 4 sig figs, so it's 24.47 liters per mole. This is going to be the 4 sig figs, or 24.5 liters per mole to 3 sig figs, or 25 liters per mole. Actually, does that round to 25? Shoot, it doesn't, does it? Or roughly 25 liters per mole. And so about 25 liters per mole. This is normally for crude approximations, we use 25, but for calculations, depending on how many sig figs we want, we'll use these two here. This is more handy to have memorized. It's more handy to have memorized because most of the stuff we deal with is at what temperature? Yeah, at room temperature. That doesn't show it there. Doesn't either. You don't really have to memorize any of these because they're easy to derive, but it's good to know it's about 25 liters per mole of gas. Under normal conditions. All right, so that's molar volume. We use this in stoichiometry quite a lot. And then 3 will be density. This is density of a gas. So the density of a gas is equal to the mass of gas divided by the volume of the gas, mass over the volume. But since it's a gas, the volume is equal to nRT over P according to the ideal gas law. And then we could substitute that in here. So this is going to equal the mass divided by nRT over P. Then we invert and multiply. And so this is going to be the mass times the pressure divided by nRT. But we recognize something here, and that is mass over moles. Mass over moles is grams per mole. Grams per mole is this symbol. What's this one again? The funny M. It's a molar mass. And so mass over N is molar mass times P divided by RT. So basically, I don't have to do any measurements. I just have to know the molar mass. So for example, what's the density of helium? Well, the molar mass of helium is 4. And so I can calculate the density of helium at any temperature and pressure. Just give me a temperature, give me a pressure, and I'll calculate it. And so let's do an example here. Example. What's the density of air? Well, the density of air is, I need the molar mass of air. Can I get the molar mass of air? Air is a mixture of nitrogen, oxygen, and other stuff. Is it possible to get the molar mass of air? Yeah, if I have a mole of air, then I'm going to have 6.022 times 10 to the 23rd molecules. 21% of those molecules will be oxygen. So how much does that weigh? In fact, didn't we calculate the molar mass of air? What was it? Does anybody remember the molar mass of air? Pure nitrogen has a molar mass of 28. Pure oxygen has a molar mass of 32, O2. So N2 is 28, O2 is 32. Which one is it going to be closer? Is it going to be closer to 28 or 32? Well, it's about 80% nitrogen. And so it's going to be closer to N2. Anybody have the molar mass? Okay, good, thanks. I needed it for this calculation. Well, that's what I calculated earlier.
But that day, you also said you were estimating from the time we did it before. It's not exact. It's in about 28.96.
Yeah. Does somebody have it written down from our calculation? I took a picture of it, and I must have deleted it or something because I couldn't find the picture of it. I was looking for it the other day. The calculation. That sounds about right. So this is going to be grams per mole. The pressure, we'll just pick normal atmospheric pressure, 1 atmosphere, or 0.08206 liters times atmosphere per mole Kelvin. And then temperature, we'll just pick normal temperature, 298.15 Kelvin. And so looking at the units, atmospheres cancel, moles cancel, Kelvin cancels, that leaves us with units of grams per liter. And so what does it come out to? Can somebody punch it out? 28.96 divided by 0.08206 divided by 298.15. 1.1836 grams per liter. We're allowed 4 sig figs, so we'll go with 1.184 grams per liter. Normal densities are in grams per milliliter, so this is about 1,000 times less dense than water.
I searched up the polarity of air, and it's 28.9647 grams per mole of dry air.
Okay,
So you're right.
so okay, that's good. That's good enough. And so it's easy. We don't have to measure anything. We can just calculate it. The other application of the ideal gas law that we do is determining the molar mass of a gas. We can calculate the molar mass of a gas too. The molar mass of a gas is equal to the grams of gas, that is the mass of gas, divided by moles of gas. Since it's a gas, then the moles of gas is equal to PV over RT. And so we'll substitute that in here. This is going to give us the mass divided by PV over RT. And this is going to equal the mass times R times T divided by PV. But when we look at it, mass over volume, we just calculated that. That was density. So this is equal to the density times R times T divided by P. Normally, when we want the molar mass of a gas, let's say the molar mass of an unknown gas, we have to feed it into a machine. The machine's called the what? What weighs molecules, individual molecules? The instrument. It is a spectrometer. 2 words though. Mass spectrometer. So we feed it into mass spectrometer. But the problem with mass spectrometer is it's expensive. And so if we could measure the density of the gas accurately and precisely, then we don't need a mass spectrometer. If we could measure the density of a gas, then we can calculate its molar mass. It's not going to be as precise as a mass spectrometer. Mass spectrometer is way more precise, but it's going to be a heck of a lot cheaper than a mass spectrometer. And so this is like the low budget way of determining molar masses. And why do we need molar masses? We need molar masses to go from the empirical formula to the molecular formula. We need to know how much the molecule weighs. And so that's the other application here. Okay, in 6.5, so I'm not going to do too many sample calculations. I just want to cover the topics, and then we can look at calculations later. In 6.5, we're looking at stoichiometry, gas stoichiometry. And so we have moles of A to moles of B. You know, this is the heart of stoichiometry, where we use the mole ratio from the balanced chemical equation to figure it out. So we can go from, for example, moles of oxygen, O2, to moles of KCl3 using the mole ratio here. But to get the moles of oxygen, we usually start off with the volume of oxygen. So we got the volume of A gas. And the conversion factor here we use is the molar volume. The molar volume, actually we have to invert it. The molar volume is going to be in units of liters per mole. So we'll just use molar volume as a conversion factor, CF. And so we'll invert it to cancel out the liters and leave us with moles. That's one way of doing it. The second way of doing it is just to use the ideal gas law. N is equal to PV over RT. It doesn't matter which one you use. And so we want the moles of A. We can just, we'll need the pressure, the volume, and the temperature. I mean, the pressure, yeah, then we can get it. If B is a gas, then we can figure out how many liters of B. And so if B is a gas, then we'll get the volume of B, which will be a gas, by the same method. One, we could use the molar volume as a conversion factor, or two, we can use the ideal gas law. Volume is equal to nRT over P. That's it. And since most reactions are done at room temperature and room pressure, then it's useful to know the molar volume because it saves you a step. What is the molar volume? Well, it depends on how many sig figs. The 3 sig figs is 24.5, right? And so an example here would be it's 1 mole per 24.5 liters. Or to 4 sig figs, it'd be 1 mole to 24.47 liters. And then we'd flip it over for this over here. This is 1 over the inverse of that. Well, these have to be gases. Or the other, this is the other way of doing this. The other way of doing this is by using Avogadro's law. If we use Avogadro's law, then we see this. that the volume is Avogadro. The volume is equal to nRT over P. Now, R is a constant, but if we have constant temperature and pressure, then this is going to be a constant times N. This means we have to have constant temperature and pressure. In other words, the volume is directly proportional to moles. So if we double the volume, we'll have twice as many moles. And therefore, rather than doing this, we could use a volume ratio. The volume ratio and the mole ratio will be the same thing because they're directly proportional to one another. And so that's the easiest way of doing gas stoichiometry. But the problem is that the temperature and pressure cannot change. And then we have it. Well, let me cover the remaining topics here. We'll look at some stoichiometry problems coming up later. Let's look at gas mixtures next. Let's say I need to mix some hydrogen and oxygen gas. How much should I mix? Well, I need 2 moles of hydrogen and 1 mole of oxygen. So how much should I mix? If I use Avogadro's law, I could say I'll mix well, 2 moles is about how many liters under standard conditions? Standard ambient conditions, not standard temperature and pressure, STP. 50. So if I use Avogadro's, I'm going to take 50 liters of hydrogen and mix it with 25 liters of oxygen. If I take 50 liters of hydrogen gas and mix it with 25 liters of oxygen gas, am I going to make 50 liters of water? No, because water is a liquid. And Avogadro's law only works for gases. That's fine. Now, what's the pressure? If I take 50 liters of hydrogen, what's the pressure? One atmosphere. If I take 25 liters of oxygen, what's the pressure? In fact, all the pressures have to be the same because Avogadro's is for constant pressure. That's different. The other way I do this is something like this. I would take 2 atmospheres of hydrogen and mix it with 1 atmosphere of oxygen. That would work too. That's called Dalton's law. If I take 2 atmospheres of hydrogen and mix it with 1 atmosphere of oxygen, then I have the correct ratio. And so let's take a look at a gas mixture here. We'll just keep it simple. Not this one. We'll look at air. And to keep things even simpler, I'm going to call air 79% nitrogen. It's actually like 78%, but we'll go with 79% nitrogen and 21% oxygen. Like that. So I have a container of air here. And are these percent by masses or percent by mole? These are percent by mole. That's correct. And so what does that mean? That means if I take 1 mole of gas, 1 mole of gas is about how many liters? 25. I'll be a little bit more precise. I'm going to call it 24.47 liters. That's 1 mole. At RT and RP, room temperature and room pressure. How many gas molecules are in a mole? Avogadro's number's worth. And so I'm going to have an Avogadro's number's worth of molecules in here. Nitrogen is blue, and then oxygen is going to be the orange. I'm going to have a lot less oxygen than nitrogen, right? And so this is the mole percentage. We also have something called the mole fraction. And so the first thing is, let's look at the mole fraction. So we convert a percentage into fraction. That's pretty simple, 79 out of 100. So that's the mole percent, this is a mole fraction. And so what does that mean? This means I have 79 moles of nitrogen for every 100 moles of air. And the other mole fraction is I'm going to have 21 moles of oxygen for every 100 moles of air. But I don't have 100 moles of air. How many moles of air do I have? One. And therefore, I can take the fraction, and multiply by how many moles. So I have 1 mole of air, and then I have 79 moles of nitrogen for every 100 moles of air. And that's going to give me how many moles of nitrogen in this 1 mole of air? I'm going to have 0.79 moles of nitrogen. And how many moles of oxygen will I have? And I'll have 0.21 moles of oxygen because I'm going to make them add up to 100%. Does that make sense? So a mole fraction is always valid. But there are two additional ways of visualizing this mixture. One way of this is removing. I'm going to remove all the oxygen out of this and only leave the nitrogen in there. And so what I'm going to do is I'm going to get 24.47 liters of nitrogen. Is it still going to be at RP? RP was 1 atmosphere. This box was at 1 atmosphere. The 1 atmosphere is due to collisions of the nitrogen and oxygen against the wall of the container. But now I've removed the oxygen, I'm going to have fewer collisions with the wall. And so what is the new pressure? Do you know what the new pressure is? So if I have 24.47 liters of nitrogen, then I don't have as many molecules. And so I have 79 molecules of nitrogen for every 100 molecules that were there. And so I'm missing a bunch. And so this is 79 out of 100 times the original pressure, 1 atmosphere. So do you know I'm only going to have 0.79 atmospheres of nitrogen? I'm missing 21% of the molecules in here. But those 21% of the molecules I'm going to put over here in this box. This box is also going to be 24.47 liters of oxygen. But there's no nitrogen in here. And so what's the pressure? So this is the mole fraction. The mole fraction times the total pressure. This is the total pressure. So we'll do the same thing. It's going to be the mole fraction of oxygen, 21 out of 100, times the pressure, total pressure of 1 atmosphere. So I'm going to get 0.21 atmospheres, 0.21 atmospheres of oxygen. So this is the way it works. This is called Dalton's law. In Dalton's law, P total is equal to the sum of the partial pressures. And so in this case, the pressure of the air is equal to the pressure of the nitrogen plus the pressure of the oxygen. And that's going to equal 0.79 atmosphere plus 0.21 atmospheres. And this is going to give us 1 atmosphere of air. But the volumes are all the same. So the volume of the nitrogen is equal to the volume of the oxygen, which is equal to the volume of the air. That's one way of visualizing it. And so if I take 24.47 liters of nitrogen plus 24.47 liters of oxygen, what's the combined volume? So 24.47 liters of nitrogen, so let's say 25 liters of nitrogen. So if I take 25 liters of nitrogen plus 25 liters of oxygen, what's the total volume? What's the total volume? 50 liters? So if I take 25 liters plus 25 liters, do I get 50 liters? No. If I take 25 liters plus 25 liters, do you know how many liters I get? 25 liters, or 24.47 if you want to be more precise. And so 24.47 liters of nitrogen plus 24.47 liters of oxygen yields 24.47 liters of air. That's Dalton's. The other way of looking at this is via Avogadro's. So let me finish with Avogadro's here. Avogadro's is we split it up like this. Avogadro's is constant pressure. Dalton's is constant volume. So we have a constant volume mixture, Dalton's, or constant pressure mixture, Avogadro's. I guess I'm out of time, so I'll just stop here. I'm going to have an extra office tonight, if you're interested. It's between 8. It'll start at 8. Go to 8 to maybe 9 or 8 to 8:30, depending on who shows up. So extra office